In this screencast, I'm going to cover descriptive statistics. This is usually in respect to samples, so samples as opposed to populations. To kind of preface this, we usually are interested in a stochastic quantity or property or variable. Stochastic meaning that the true values are statistical and they behave according to a distribution function. So this population has some sort of distribution. Obviously, you cannot know all of the values of the population. In other words, if I wanted to calculate the average height of all Americans, if I wanted to get that exactly, I would have to measure the height of every American, which obviously is not possible. Instead, we take a small sample, we take measurements, and hopefully our sample is a true representation of the population. There arises an issue. How big of a sample should you take such that your sample is representative of the population? There's always a chance that your sample is not going to be representative of the population. After we take a sample, we usually generate sample statistics and diagrams. We also then try to analyze the type of distribution, its parameters, and its uncertainty. So in this screencast, I'm just going to cover how we can calculate descriptive statistics for our sample. Some of these you've already been exposed to. We have statistics for the central value, also known as the central tendency. The most common by far is the sample mean, also known as the average, and we see that denoted a lot of times by X bar. The median looks similar, but on top of the X there we have a tilde, so be sure that you make note of that. The mode is the most frequently occurring value. There's also some other things that we're not going to talk about too much in this class. M estimator. This is a robust estimator and it removes the effects of outliers. You're also interested in looking at the dispersion or the variability in your sample. The most common of these by far is the sample standard deviation. We denote that by S, and you guys have seen that. There's also the range, which is the maximum minus the minimum. Obviously, if you have a really dispersed sample, you're going to have a really big range, and if you have a very non-dispersed sample, your range is going to be small. Some people will use this measure of dispersion known as MAD, the median absolute deviation. There's some others that I'll show you related to how symmetric the distribution is. That's skewness. It shows the asymmetry of the distribution. If a distribution is skewed one way or the other, then you're going to get a negative or positive skewness. For example, if we had a distribution like this that had a long tail to the right, that would have a positive skewness. A long tail to the right would represent a negative skewness. These are relative to a normal distribution. Kurtosis shows the peakedness and flatness of a distribution compared to the normal distribution. If you had something that was really sharp and peaked like this, then that would have a positive kurtosis. If you had something that was relatively flat compared to the normal distribution, then that would have a negative kurtosis. We can compute the sample mean or the average using the average function in Excel or by hand using this formula. It's just the sum of all of your X values divided by the number in your sample, little n. The sample median can be computed using the median function in Excel. You sort the data and then it's the very middle value. If you have an odd number, then that's easy. For example, if you had 7 numbers, you just choose the fourth. If it's an even number, you just take the average of those two. For example, if we had these data and I sorted from lowest to highest, I have an even number, so I would just take the average of those two and my median would be 5.5. Sample standard deviation, note the division by n minus 1 here. And that's important compared to population standard deviation, where you just divide by n. In Excel, you can use the stdev.s function for sample standard deviation. We can also compute the range by determining the max and the min and the difference between those. I want to just briefly explain the difference between sample and population statistics. Oftentimes you have a population of size big N, and you're just taking a small sample to estimate parameters of the population. Sample size is usually denoted by little n. The mean, the actual mean of the population is generally denoted by mu. The mean of your sample is X bar. The actual standard deviation of your population is sigma. The variance would be sigma squared. An estimate for sigma based upon your sample is the sample variance, s squared, and the sample standard deviation, which is the square root of s squared, and that's just s. And so we use little n, x bar, and little s to sort of represent, hopefully, your much larger population that has capital N items, has an average of mu, and it has an actual standard deviation of sigma. So I've got a file here called Old Faithful. If you want to work along, I'm just going to real quickly compute some of these things. The first thing I'm going to do is I'm going to select B6 all the way down to the bottom by doing Control-Shift down, and I'm just going to call this data, just to name that. Let's compute a couple of things. First of all, the count. You can always use the count function of data if you want to know the number of items. It's a quick way to do that. The average, we can simply do average of our data. There's a median function. We can compute the median of the data. There's also a mode function. We can compute that using mode of our data. The standard deviation, we want to make sure if this is a sample and not the entire population, it would be rare that you use the .p version. So this is a sample standard deviation. Again, the difference between .s and .p, in .s you're dividing by n minus 1, in .p you're dividing by n. As your sample size gets bigger, it's not as big of a deal. But we can do that for our data. We can compute the minimum of data. We can compute the maximum of our data. The range is the max minus the min. And let's just compute a few more things here. The skewness and kurtosis, we can use the skew function of our data. There's the kurt function. This is telling us that compared to a normal distribution, it's going to have a tail slightly out to the left, and it's going to be slightly flatter than a normally distributed variable. So hopefully this screencast kind of gives you a better idea of descriptive statistics and the difference between population parameters and sample parameters. Thanks for watching.